Hey guys, so this is the 7-1 video, which is over exponential function. This is completely review from what you've learned in Algebra 2 and pre-calculus last year.
Austin Edwards, please come to the office. Austin Edwards.
Excuse me. Okay, so all you really need to remember or refresh are these different properties. Okay, so remember that anything to the 0 power is 1. If you have a to the x times a to the y, you add those exponents. If they're being divided, you subtract the exponents. If you have an exponent to another exponent, that's when you multiply. For case 5, idea is just distribute this exponent. It has to be go into both exponents. Same thing with dividing. And then a negative exponent just simply moves it into the denominator. And the last one, this is just a basic rule, or maybe a don't do rule. You can't just distribute an exponent if you have a quantity. You would have to FOIL it instead of distributing it. So that's a common mistake that we see. Okay, so we'll just do a couple of these examples. Starting with number 1, if you have 27 to the 4/3, remember that the bottom number is your root and the top number is the exponent. Okay, so this will basically break down into the cube root of 27. Whoops. 27 to the 4th power. Okay, and the cube root of 27 becomes 3, and then you have 3 to the 4th. So 3 to the 4th would be, let's see, 9 times 9, which is 81. Okay, number 2, immediately I see to the 0 power, and I'm going to stop there and go, that is definitely 1. Okay, when you get to number 3, I'm going to start by simplifying the inside. You can go about this a couple different ways. You could distribute that exponent and then subtract, but I'm going to ignore the exponent on the outside. I'm going to start by combining the top piece. So I'm going to add the exponents for that. So it gives me e squared over e to the 4th. And then I'm just going to subtract the exponent. So you can write this one of two ways. You can just bring it up and say e to the -2, or you can just leave it as a fraction form, which is what I'm going to do. So since it's bigger on bottom, you subtract those. And now you're going to multiply, or not multiply, but have the exponent go to the 1 and also to the e squared. So 1 squared is 1 and e squared squared. Multiplying those gives me e to the 4th. Okay, number 4. This one we have two different bases. We have a 5 and a 25, but immediately I noticed that you can rewrite 25 as 5 squared. So we can say, since 25 is 5 squared, we can write it that way instead. And then we would have 5 cubed and then multiply 2 times -1.
There was a flash drive left in the library that has Ruby documents on it and Ruby pictures, and I have it in the office. If it is yours, please come to the office. It is a flash drive with Ruby documents and Ruby pictures on it. Thank you.
Sorry about that. Okay, so now we're going to put that into the bottom because you have a negative exponent, so 1 over 5. And when you move it, realize that the negative exponent goes away. Okay, so for question number 5, now you're solving an equation without using a calculator. The best way to do this is, let's see, there's a couple different ways you can go about this. You can convert it into logarithmic form, but that wouldn't help because you still can't use a calculator. What you want to do is try to get the same base involved. Okay, so if you're looking at 9 and 27, both of those are multiples of like 3. Okay, so 3 squared is 9, and 27 is the same as 3 to the 3rd. So this right-hand side, if we multiply those two exponents, is 3 to the 2x, and that's equal to 3 cubed. And now, since these bases are the same, we can just set the exponents equal to each other and just solve that. So this gives us an x of 3/2. Okay. For this one, we can go ahead and draw this using a calculator. Okay, so I'm just gonna pretend that you watched me type this into a calculator and just keep going. Basically, remember that E is the value 2.718, okay? So all three of these functions have a y-intercept of 1. They're both growths. The difference is that one is more steeper than the other. So the flattest one is going to be the one with the 2 as your growth rate. So that's your first one. That's going to be the most flat. Okay, then the next one, 2.718, will be slightly steeper than that. So it'll really start out exactly the same, but just grow quicker. So this is e to the x. And then the last one, to the 5th, that one has a faster growth rate than that. So again, same idea, but growing faster. Okay. So do these graphs look similar? Absolutely. They're like all identical, but the different growth rates make them grow faster. Okay, so you could say something along the lines of they're all growths, exponential growths to be more precise. They all have a y-intercept that's the same at 1, and they all have horizontal asymptotes at 0. Okay, so all very similar functions, just one they have steeper slopes. Okay. So the second part of this is, hopefully you remember this from before, exponential growths. In the past, I have taught this as y is equal to a times b to the x, where a is your y-intercept and b is your growth factor. Okay, so the growth factor all depends on the value. If the b value is greater than 1, then it's a growth. Okay, so the graph of that is just like those ones we just did, would go up. If it's less than 1, but it must be positive, so it has to be greater than 0, that's a decay. So that graph starts high and goes down towards the horizontal asymptote. Okay, so these all have horizontal asymptotes at y equals 0. Of course, unless the whole function is moved up or down. They're continuous. They're all concave, whatever it is. So a growth is going to be a concave up. A decay is a concave down. This is a new little concept right here. We knew the y-intercept, but here's a key point. 1a is a point on the line. So we can use that to help be more accurate with our graphing to make things quite simple. Okay, so if we were going to graph this without a calculator to be quite accurate, we can say this has a y-intercept at 0, 1. Okay, and then it has a point at 1, e. Okay, so remember e is 2.718. Okay, so I can plot those points. We got 0, 1, and then we got 1, 2.718-ish. Okay, so we got a horizontal asymptote, and then we have this growth up and to the right. Okay, so if we take that same idea and now have a quick translation of +1, a +1 on any graph is going to move it up 1 unit, which means our horizontal asymptote is going to go up 1 unit. So I'm going to draw a little dotted line for my horizontal asymptote at y equals 1. Okay, and this time my reference point, like it's going to be the same as these, but up 1 unit. Okay, so we're going to have a y-intercept at 0, 2. Okay, and then for the second point, so you can kind of think of this of a couple different ways. You could plug in 1 into your function. So if I plug 1 into the x, I have e to the -1 plus 1. Let me write what I'm trying to say. Whoops. It's 1. So e to the negative 1 plus 1, okay, is 1 over e plus 1. So maybe that's not a very good helpful point, because what exactly would that value be if we were graphing it? So let's just use the idea of if I have a negative in front. So what is that going to do to any function? If it's inside with the x, that's going to flip it over the y-axis. So basically, if we normally start here and go up, okay, that's going to go flipped over the y-axis, and it's going to go up and then down towards that horizontal asymptote. Okay, so those are your basic graphing. Okay, so just kind of a refresher on all of these ideas. Mostly I want you guys just to remember those basic rules of exponents. So I would like for you to do problems 1 through 18 by the next time I see you. Okay,